in review what we talked about. We are building up the necessary tools and reasoning skills to believe the first derivative test, the second derivative test, and all this other stuff. These are things that we've been told are true, and I want to give, again, reasons why they are true. And in order to do that, we need to know things like Rolle's theorem, Clairaut's theorem, and the mean value theorem. So Clairaut's theorem, again, theorem says that F smooth and F of C a high point then for sure. Who said that? Excellent. So test-wise, is this test where the conceptual questions just come all of the time? Right? So what we're required, again, in order to do conceptual questions right, there was only like a few people in the last test that just crushed everything and then got wrecked by these types of questions, right? So my advice is that to again learn the street version. Right? Learn the street version, right? So Rolle's theorem says that if you start and end at the same place and you're smooth, then you have to stop somewhere in between, right? So Rolle's theorem says that F smooth, and you start and end at the same place, then there exists a C between A and B, where F prime of C is equal to 0. Question number X on the test is state the mean value theorem and draw graphical representation or interpretation. State the mean value theorem and draw a geographical interpretation and give a geographical interpretation. That's usually how I say it over the years. Yes, please. I can't, thank you. Wait, go up this way? Yeah. Thank you. Yeah. State the mean value theorem and give it a geometrical interpretation. That's how I say it. And give a geometrical interpretation. Okay.
Dr. Wayne?
Yes.
So is the mean value theorem like either of those?
No, I'm about to state it in just a second. Thank you. This is due to Cauchy, one of the great mathematicians. We'll use the mean value theorem to prove L'Hopital's rule. We use the mean value theorem to do a bunch of stuff with the integral. We're going to use the mean value theorem to prove something we've been saying over and over and over again. So again, Rolle's theorem says that if you have a graph here, it starts here, ends here, then somewhere in between here and here, here's A, here's B, somewhere in between there is a, I should use a different color, there is the slope of the tangent line here is, I'm sorry, the slope of the secant line here is 0, there is some point in between, this looks like the midpoint in this particular case, where the slope is exactly the same. The mean value theorem says that, this is not, there's nothing that stops me from rotating this graph, so that if I give you any function between f of A and f of B, then there's some place in between that's going to be parallel to this, right? So, and it looks like it's right here, right? Looks like it's that C right there where the tangent line is the same as the secant line. All right, that is the graphical geometric interpretation I'm looking for. It is that. I'm going to open up the floor. I want to be fully transparent so that there's no confusion about what I'm asking for a geometrical interpretation. So there are very few times in which I get heated. This is one of those times where I say, this is what I want, I look what seemingly looks like everybody in the eye and say, this is what I want. And then someone goes up there and writes Mandarin on the test, right? So do not do that, right? So this is going to be 5 points on the test to draw a graph, starting in one place, ending in another place. Draw the secant line. If you give me a graph that's smooth, you should find a place in between where the tangent line is parallel to the secant line. Okay? Please.
Which theorem is that?
I haven't stated the theorem yet, but it's the mean value theorem. So let's go ahead and say, so again, I like to motivate why a theorem is true. So that is the picture of the following thing. That's the picture of saying that if I give you the mean value theorem, whew. And so the mean value theorem says that let f be differentiable. So we need a smooth function, differentiable on a to b, and f continuous on the closed interval a to b. Then, and again, it's going to look a lot like Rolle's theorem. There is a C between A and B with the following property. What property is that? We'll draw the picture again. We'll do that, right? And so here's A, here's B, here's f of A, here's f of B, secant line. Looks like there are a bunch of C's for this one. I just need one. Looks like it's here maybe. Looks like there are 3 at least. This one there, looks like there's one here and there's one there, where the tangent line is parallel to the secant line. Well, when 2 lines are parallel, what does that say about the 2 lines? The slopes are equal. Oh, have mercy, right? So this is f of A, this is f of B. We know the slope of that is f of B minus f of A over B minus A. And we're claiming that there's a place where the slope of the tangent line is the same as the slope of the secant line. Here's the slope of the tangent line. What's the slope of this line? That's close. Let's use the right terminology. This is f, right? This is the slope of the tangent line at C. F prime of C. That is the mean value theorem. So we'll give all sorts of street versions for this. Say it again. Go ahead.
Why did you write f continuous?
That's a great question. So I need it because I need to talk about the endpoints, right? So I just wanted to make sure that, so notice how I have f differentiable on the open interval and f continuous on the closed interval. So I need the closed interval, I need f to be defined at a and b. Yeah. Go ahead.
So what's the rest of the purple part of the mean value? Is it the part in red at the bottom?
Well, I'm sorry, say that again?
Because you didn't really finish what you wrote in purple, so I'm asking if it's the part in red that's the end of that statement.
Oh, it's this. There's a C between A and B with this property.
Okay.
Yeah.
Thank you.
Yeah. This is the conclusion of the mean value theorem. That the slope, so this is the slope of the secant line connecting the 2 endpoints is the same as the slope of the tangent line. I have a continuous function on the interval a to b that's also differentiable on the open interval a and b. Is there a place between a and b where the tangent line at C is the same, it's parallel to the secant line? Yes or no? Yes.
Yes.
Yes, that is exactly the mean value theorem. And I know this trepidation of, wait, did he say everything that needed to be said? Did he leave out something that needed to be said? Right? So good. So when I ask a true false question about this, make sure that f is continuous, differentiable. AB is what type of interval? Closed. Okay, excellent. Good, good. Okay. Questions on this? Why does the mean value theorem imply Rolle's theorem? If I make what? What could I do to make this easily Rolle's theorem?
Make the slope of the secant length theorem.
That's right. Make it, or make. That's right. Right. So if this is true, then Rolle's theorem follows if you just make f of b equal to f of a, which just means to go back to this graph and just rotate it back, and it looks like this, right? So these statements are completely equivalent, right? If you have this, then this follows simply by doing a transformation. If you have this comes from that simply by making f of a and f of b the same. They're the same statement mathematically. Very, very good. All right, so let's do one in application. So I'm sorry, I'll take any other questions about the mean value theorem. Yes, go ahead.
Like why does mean value theorem like have to be a separate theorem if it's like technically?
That is a great question as well, and it's only because in this form it helps us prove things. So I'm going to prove L'Hopital's rule, and proving L'Hopital's rule is much easier to use the way that it's written here than using Rolle's theorem. Yep, that's exactly right. Yeah. So it's just cosmetic. If f prime of x is equal to 0 for every x, then what do I know about f? F is constant for some c and r. What does the symbol again mean? In the real line, there's some real number that f of x is always equal to, right? So the great skeptic has been so nice to us. We've said this so often, and then now she comes in and says, look, you keep saying that if f prime of x is 0 for every x and f is flat the whole time, how do I know it's not something else? How do I know it's not something else? Okay. Here's the proof. That's a claim. Here's the proof of that. How do I show something's constant? How do you know if something's constant?
It has the same y value for everything. So.
Absolutely right. Right. So that if I give you f of x equals 7, I know that's constant because if you give me 12, it's 7. You give me 13, it's 7. You give me 4.28, it's 7. Right. For every x and every y, what do I know about f of x and f of y? You give me f of x, you give me f of y. What has to be true for if f is constant?
They're equal.
They have to be the same, no matter what x and y are, and that's what we're about to show, right? So we show for every r and s, f of r is equal to f of s. That's what we're going to show. And if that's true, then I know then it's constant. We're going to assume f is differentiable in the whole real line. Does that make it continuous? It does, right? So if f is differentiable in the whole real line, then it is continuous. All right, so let r and s be given. We're going to show that f of r is equal to f of s for f. On the interval, and which one for without loss of generality? Let's make them different. Which one's bigger? R. Okay, so suppose r is bigger. Okay, so let r be bigger than S. Then on the interval S to R, F is continuous. F is differentiable. What can I invoke? What can I use? The mean value theorem. So by the mean value theorem,
Can you write MVT?
you can. I will eventually. By the mean value theorem, what do I know? There's a
C.
C.
Manageable S and R.
There's a C between S and R such that what? F prime of C is equal to F of
F.
no, F of R minus F of
F.
all over
R minus.
R minus S. I know it's thrilling. So that's the mean value theorem. Some people like to write it like this. F prime of C times R minus S is equal to F of R minus F of S. Some people like to write it like that, right? So you just move the denominator to the left-hand side, multiply both sides by R minus S. What do I know about F prime of C? Why? Because it said so. That's right. Excellent, brother. We assume by hypothesis this is 0, and therefore 0 is equal to F of R minus F of S. And thus F of R is equal to F of S. And what do we say about R and S? What do we say about R and S? Did we say anything special? R is greater than S, but did we say anything special? Nope. Nothing special about R and S. You give me R, you give me S, F of R and F of S are the same. We didn't say anything special about them except that we're different. Any two R and S's you give me, F has to be the same for F of R and F of S. That means F is constant. And thus, F is constant. Right, so that is the proof. We've had this street version for a long time that if the derivative represents the rate of change and I come across a function whose derivative is always 0, then it makes complete sense why that function should always be constant. We have now shown that by the mean value theorem. Okay? Questions about that? There'll be some extra credit on the way in just a second. Here's a real one we've been saying over and over and over again. If f prime of x is positive, then f is increasing. I've been saying that over and over and over again. You've been so nice to me. I never showed that that was true. You might imagine what the extra credit will be. We showed that if f is increasing, then f prime is positive. If f is increasing, f prime is positive. Now, if f prime is positive, then f has to be going up. So what does this mean now? This means that I could show you the derivative. Someone asked this question earlier, I think. If I show you the derivative, what does f look like? Right? Before we were saying, here's f, which one of these is the derivative? Now I can show you something that had the derivative of something, and then you should be able to tell me roughly what f is. Okay. What does it mean to increase? If I give you any r and s, if r is less than s, what do I know about f of r and f of s? f of r is less than f of s, right? So I want to show, we need to show, this is the definition of increasing, that if r is less than s, then f of r is less than f of s. That's the plan, right? So we'll let r and s be given with r less than s. Well, f is differentiable and continuous. F is continuous on the interval r to s. F is differentiable on the open interval r to s. So by the mean value theorem, there is a C between R and S such that f prime of C is equal to f of R minus f of S all over R minus S. Wait, which one's bigger? S is bigger, right?
Yeah.
So f of S minus f of R over S minus R. I want to show f of S is bigger than f of R. What do I know about f prime of C? What do we say about this? It's greater than 0. What do we know about S minus R? How do you know? Because R is less than S, and therefore this is positive, this is positive. What about this? That also has to be positive. Writing it as we said before, f of S minus f of R is equal to f prime of C times S minus R. This is positive by hypothesis. S is bigger than R, that's positive, and therefore f of S minus f of R is greater than 0, in which case f of S is bigger than f of R. So whenever S was bigger than R, f of S is bigger than f of R. And that means f is increasing. I don't need to tell any of my people who aren't happy with their grade that extra credit is a way to catch up. If f is decreasing, then if f prime is negative, then f is decreasing. This color needs to go. What color is that? Is that like a dark green, or is that just black? Is that just black? Okay, great. This one's not. Yeah. So, extra credit. F prime negative implies f is decreasing. Even or odd? Yeah. Yeah. Even or odd? Even? Make it worth 4 points. This should be a straightforward 4 points. Jessica's gonna be so mad at me. She's gonna be like, well, you're giving all this extra credit. I'm here to say that my name is Eric Swinger and I have a problem. I've been saying that for years and it still hasn't helped. I'm just addicted to giving extra credit. Go ahead.
The portion of extra credit you gave us was like 3 points. And that was like the longest like work I had to do.
Well, because someone said odd, and if they said even, I would have said 28. I mean, that's not. I mean, that's not my fault, right? So, yeah, they just picked the wrong number. So, no, sometimes it happens. And what's interesting is that I have such a problem that I'll say I'll give this for extra credit, and then some people start groaning for extra credit, for extra credit. That's how bad it gets sometimes. Okay. Questions about what I'm asking? Questions about this proof, any of these steps? You'll need to mimic some of these steps, obviously. Be right. Just be right. Okay, great. Anything else? So we're good. So now let's be clear that now we have a bunch of if and only if statements. If f is smooth, if f is differentiable on the whole real line, we have now completed the full circle that f is increasing if and only if f prime is positive. F is decreasing if and only if f prime is negative. And f is constant if and only if f prime is always 0. So now they go both ways. So that now we are good to go in terms of being able to talk about all sorts of things now. Okay, so this is the time where we can now talk about the first derivative test. Absolutely. Let's do an example. Let's do something like, let's do something like x squared minus 2x plus 7. Start with a nice function like this. We can say a lot of things about this without doing any calculus. I tend to do an example we're all familiar with so we can get all the principles out so that when I give you something that's ridiculous, we're still doing the same thing. Okay. So what I want to do is I want to find a local max or a local min. Street version, I'm looking for all the humps. I'm looking for all the humps. That's right. That's what Clairaut's theorem says, right? I have one of the nicest functions I could ever come across, a polynomial, beautifully continuous, no jumps or breaks. It's smooth as possible. I can take derivatives forever, right? So Clairaut's theorem says that if you are smooth, then any local max or min has to have the property that the derivative there has to be 0. And so in order to find one of those places, it has to make the derivative equal to 0. And so any place that makes the derivative 0 might be a place where this happens. Right? So that's why when you do all this, that's always the first step. Set the derivative equal to 0 and solve. If you're looking for humps, then the derivative needs to be 0 there. So let's go ahead and set the derivative equal to 0 and solve. Right? F prime of x is equal to 2x minus 2. You set that equal to 0. You get 2x is equal to 2. And x is equal to 1. What do I know about 1? At 1, it's, what did I just show? At 1, it's what? Which means, well, what's the street version? That means that f is flat at 1. Okay? So we're going to use some calculus and some non-calculus to see what's going on at 1. But we know only one of 3 things can happen at 1. I know wherever, well, at 1, what is it? It looks like it's 6, right? At 1, it's 6. 1, 2, 3, 4, 5, 6. This thing's nice and smooth, and we know that at 1, it's flat. The tangent line is horizontal, and we know it's doing one of 3 things, basically, or one of a few things. Either it's doing this, it's doing that, or it's doing what? This, that, all sorts of things, right? The first 2 I wrote makes it a local minimum and a local maximum, respectively. The other 2, those wiggly things, right? Those x cubed type things, it's neither, right? Which one is it?
Minimum.
Minimum? Give me a non-calculus reason why this is a minimum.
Because the a value for the quadratic is positive.
That's right. This is a quadratic, right? Here, this number is 1, and so that means it opens up. So if you know something specific about the function, then you can make a remark about that this is the vertex, the coefficient of a is positive, it opens up, right? So, or you can make the argument that the degree is 2, so what does it do to the left and to the right?
They overlap.
Yeah, so it rises to the left and to the right. Right? So that means that the number in the middle has to be smaller, right? As opposed to, so it's only going to do this or this because of the quadratic, right? So that's the non-calculus reason for this specific function. Obviously, we're going to give you all sorts of ridiculous functions that you can't make the argument about because we won't know anything about them. Because if we knew everything about every function, why would we be doing this, right? So there are going to be some functions that we just won't be able to make that analysis. This is why calculus is useful, right? What's the non-calculus? What's the calculus reason that we're going to come up with for why this is a maximum? I'm sorry, a minimum. How do we know it looks like this, right? So the calculus reason obviously has to do with derivatives. And we alluded to this earlier in this semester or in this session, that we're going to say something about the derivatives on this side and something about the derivatives on this side. Namely, we're going to say, yo, this is decreasing before and increasing afterwards. Right? That's a statement about the derivative, and that's why we call this the first derivative test. The first derivative test, the street version says, all I want to say is that the way to convince the great skeptic that 1 is a local minimum, in this case it's the absolute minimum, but that it's a local minimum, is that I'm going to convince him that the derivative before is negative, the derivative after is positive. Once he believes that, because of the mean value theorem, I know that a function that has a derivative that's negative before has to be decreasing before. And a function that has a derivative afterwards has to be increasing afterwards. And so because this is smooth, 1 itself has to be a local minimum. And so the way that we do that is I care about the sign of the first derivative. So we create a sign chart. Now, I have seen people use tables for these things. Whatever makes you happy. I need to understand the sign of the derivative. Now we did something like this earlier. I was hinting towards this very moment where we invoke the intermediate value theorem to suggest that we can pick points on both sides of the number 1, and whatever number we get when we plug into the derivative represents the sign for the entire interval. We're going to pick a number bigger than 1 and pick a number less than 1. So our job, which seems impossible, is to understand what happens to 2x minus 2 after 1. And again, we make the audacious claim that I just need to pick one value, and that value will tell me the sign forever. So when I plug in 3, f prime of 3 is 2 times 3 minus 2. That is 4, which is positive. And so that means that this is positive. The derivative is positive after 1 forever and ever and ever. And that, again, is because if the skeptic comes in and says, no, I think it's negative somewhere, because we found out that it's positive one place, and then you want to claim it's negative somewhere else over here, that, of course, means that it has to cross the x-axis. And that's a big no-no, because we already found where it crosses the x-axis. So this has to stay positive the whole way. And similarly, f prime of 0 is 2 times 0 minus 2, which is a very negative number. And so this is negative on this side. So I did a sign chart for the derivative of f. I now have it as the case that f prime is negative before 1, it's 0 at 1, and then it's positive after 1. That means, by the mean value theorem, that f is decreasing before 1, it's flat at 1, and then it's increasing after 1. That makes 1 a minimum. I'm now going to state the first derivative test. So let's talk about terminology while we're here. So a local minimum occurs at x equals 1. The local minimum is f of 1, which we said was 6, right? 1 squared minus 2 times 1 plus 7. 1 minus 2 plus 7, 6. Just terminology, right? So that the local minimum occurs at 1. 1 second is the time where the minimum occurs. The minimum actually is 6. Right? The local minimum is the number 6. Okay. Questions about that? Let's state it. The first derivative test. Let f be differentiable. And f prime of c is 0. Then, if f prime of x is less than 0 for x less than c, and f prime of x is greater than 0 for x greater than c, then f of c is at least a local what? That's a local minimum. If f prime of x, if f is increasing for x less than c, and then it starts decreasing when x is bigger than c, then f of c is a local maximum. Please. Oh, thank you. Yeah. Questions there?
So this is the definition of first derivative.
Say it again?
This is the definition for the first derivative.
This is the first derivative test. This is the first derivative test, right? So it's a way of using the first derivative to test whether a particular, what we call these critical numbers, right? So C is called a critical number. So Clairaut's theorem says that if you're looking for a place where the humps are, then I know at those places that the derivative is equal to 0. And the question is, well, okay, you just told me it's flat. You didn't tell me whether it's a max or a min or neither. And so we need a way of testing whether it's a max or a min or neither. And we use the first derivative to test that. And that's why it's called the first derivative test. Questions there? F of x is equal to x plus 1 over x on the interval 0 to infinity. You can get a graph of that. X plus 1 over x. We're about to graph it. We know that this has a minimum on the whole real line, on the positive x-axis, I should say, on this domain. How do we know that? What happens when x goes to 0? What happens to this? 0 from the right. What happens there? Yeah, it goes higher and higher, right? When x gets really, really small, as x goes to 0 from the right, this gets super small and that goes higher and higher. And of course we know that as x gets larger and larger and larger, what happens to this? But what happens to that? It gets bigger. So now we got something that as you move to the left, it goes higher and higher and higher. As you move to the right, it goes higher and higher and higher. But this thing is continuous and differentiable. So I got something that's smooth, that on the endpoints of its domain is getting higher and higher. It seems like something's got to happen in the middle. Right. So this is going to have a minimum. What is it? So all we're doing is demonstrating that. And again, we got so much technology to go ahead and aid us in this. We just need to demonstrate that it's this thing, right? I've been biased, I've chosen the right-hand side, right? So we can obviously find this point as well in the same way. Right. You could probably use some symmetry to also demonstrate this. Let's find this point 1, 2. Demonstrated that as a local minimum. Of course, this is a local minimum because in this area, this is the lowest value, but clearly this is not the lowest value on the entire domain if we extend it. This is the lowest value on the interval 0 to infinity, 0 not included. This requires, again, that looks like 2, right? We're going to look at where the tangent line is equal to 0. Right? And that's at 2. Y equals 2. Right? Or that's at x equals 1, and the line is y equals 2. Right. F prime of x is equal to, we want to take the derivative set equal to 0 and solve. The derivative of x is 1. The derivative of 1 over x is negative 1 over x squared. I need that to be 0. Any questions about that? We haven't done this enough, but the derivative of 1 over x, this is because the derivative of 1 over x is the derivative of x to the minus 1, which is minus x to the minus 2, which is minus 1 over x squared. So that's just the power rule. One minus 1 over x squared is equal to 0. 1 is equal to 1 over x squared. X squared is equal to 1. What's x?
Plus or minus.
It's 1, or x is minus 1. Yeah, I was a tyrant, and I only wanted to know about this interval. So that is not one of the ones that I'm interested in. So x equals 1. So I know. So now I've shown that it's flat at 1. The question is it a max or a min? We now have that the derivative is 1 minus 1 over x squared. Here we found the number 1, right? Say it again. Right, so now I'm going to put a 0 here. Why? Because that's the boundary. Right. So I haven't picked, so I'm not going to pick 0, but I can only pick a number between 0 and 1. So before, when the function is defined on the whole real line, I can pick whatever values I want to the left and to the right of 1, but I have to pick a value that's in the domain. Please.
So, like on our next test, do you want us to show that we still find -1 and just not use it, or you just like? Yeah.
That's a good question. So the greater, so if you write x squared equals 1, and that means x is 1, then it's hard not to think that you didn't know this, right? So this means this, right? So yeah, we probably want to see both of them and that you cross out 1. Yeah, for sure. Yeah. Only because this is a problem that people have over and over and over again, that people forget the minus. I would like to see the minus. That's about as tyrant-y as I'll get. So, okay, so great. So we'll pick a value here. 1/2, 5,000. F prime of 1/2 is equal to what? I'm sorry. Let's just make sure. 1 minus 4 is negative, right? 1 minus 1 over 1/2 squared. 1 minus 1 over 1/4. 1 minus 4, negative. Should be decreasing before 1. F prime of 5,000 is 1 minus 1 over 25 million. That's positive. It's increasing after 1. F of 1 is a local minimum by the first derivative test. Questions about that? It's straightforward. So the challenge for these will be simply how bad is this step solving this? That's usually the only challenge. How bad is solving that? Questions? Okay, excellent. Let's do one that we did earlier. G of x equal to x e to the minus x. Where are the humps? The exponential is continuous differentiable, so is x. When you multiply, you get something that's continuous and differentiable. Where are the humps? X e to the minus x. Let's see how good this thing is. X e to the negative x. That thing right there looks like it's 1. What's the y value? What's the y value? G prime of x. Rule. Product rule. Product rule, chain rule. UV, U prime V plus V prime U. The derivative of U is 1 times V plus the derivative of V is e to the minus x times minus 1 times U, which is x. I need that to be 0. E to the minus x e to the minus x is equal to 0. And here's where people get terrified and all this other stuff, right? So factor e to the minus x times 1 minus x is 0. And this implies that either e to the minus x is 0 or 1 minus x is 0. And of course, we'll remark that this is not possible. And so x is equal to 1. There may be some trepidation with playing with this derivative. There should not be. When I write the derivative, I probably want to write it in the nicest form to pick values. This is usually, factor form is usually the best way. Please go ahead.
You have to write like not possible.
You have to cross it out. You have to do something. Yeah, you have to say why is it that you are not including that one. I definitely know that from seeing Jessica Gray. So she definitely wants a reason as to why you're not doing that. We'll pick some values. This is easy, right? 5, 0. This is defined on the whole real line, so you get to pick whatever values you like. Positive. What's going on here? Oh, I'm sorry. This is negative, right? Maybe that's what's going on. Negative, positive. F of 1 is a local maximum. In this case, it's an absolute maximum, right? But we'll talk about that. This is what's going to happen eventually. I'm going to say pick values, put it into the derivative, and I'm not going to do it, right? So I'll do it this time. G prime of 5 is equal to e to the minus 5 times 1 minus 5. That's minus 4 e to the minus 5. I don't care about e to the minus 5. I just know that it's positive, and so minus 4 times that is negative. G prime of 0 is a beautiful 1. It's e to the minus 0 times 1 minus 0. That's 1 times 1, which is 1, which is positive. So you will be given all sorts of functions. Take a derivative, set it equal to 0, create a number line. Yeah, and it should work out nicely for you. Any questions about this in particular? All right, I have been super biased about derivatives in the sense in the following sense. I can talk about the derivative of this. F is a function. F prime is a function. I could take the derivative of that. Right? Okay. So then the derivative of this of F prime. What is that? 6x. 6x, right? Is that okay? I'm going to come up with notation for that. Every prime represents a derivative. Okay. Every prime represents a derivative. So f double prime means that I've taken f and I've taken two derivatives. Okay. What does f double prime represent? Acceleration. Okay, I'm hearing all sorts of things, right? So if f represents distance, right, then its derivative represents velocity, how the rate at which the distance is changing. That's velocity. And then its derivative represents the rate at which the velocity is changing, and that's acceleration, right? So the second derivative has applications to physics and so forth, right? But as it stands right now, f double prime, as we see, only represents the rate of change of what? The rate of change of the rate of change, right? The rate of change of the rate of change. So the street version right now is that this is the rate of change of the rate of change. I'm going to draw a function f I'm going to draw another function g. Here is F. Here is G. Tell me about F prime. Positive. Questions on that? Why is F prime positive? F is increasing. Tell me about G prime. Positive. So F prime is positive. G prime is positive. Excellent. Tell me about F double prime. Tell me about the second derivative. Tell me about F double prime. So what can we say? Think about this. I love pre-programmed people. I just love it. I just love it. Why?
Because if F prime represents the velocity,
F prime is the velocity.
and that's F prime is going to, even though F prime is greater than 0, it, like as the graph F like goes on, like F prime kind of decreases or gets like smaller than it was before.
That is correct. That's right. So what is F double prime?
Sorry.
No, but what is it?
Negative.
No, but what is it? What's the street version for F double prime?
Rate of change.
It's the rate of change of the rate of change, right? So what we're asking is, how is what changing? The slope. F double prime measures how the slope is changing. Go ahead. The
slope is constant.
the slope is constant for what? For this graph? That's okay. Okay, I'm just trying to understand. Okay. So F double prime measures how F prime changes. F double prime measures the rate at which this is changing. This is the slope. So this measures how the slope is changing. And then when you look at the slopes here, right? I need a better green color, right? So what's happening to the slopes? Right? The slopes are decreasing. Yes? Now why is that the case? Because the graph looks like it's doing what? Getting less steep. It's getting less steep. F double prime is negative. The slopes are decreasing. If the slopes are decreasing and the derivative represents the slope, that means that the derivative of the derivative should be negative. If the slopes are decreasing, the second derivative is negative. Similarly over here.
You say slopes are negative? Or slopes are decreasing, second derivative is negative?
If the slopes are decreasing, then the second derivative is negative. That's right. Now notice it has nothing to do with the sign of F prime. And oh my goodness. In conceptual city on the test, I got all sorts of crazy things about F prime, F double prime, F being positive, F prime being positive, F double prime being positive, right? So be ready. So we'll spend some time talking about all of those things. In a similar way, G double prime is positive over here because the slopes, this is getting more what? It's getting steeper, right? So that the rate, the slopes are increasing, so that means that the derivative of whatever might be the slopes has to be positive, but the slopes are measured by the derivative. So the derivative of the derivative is positive. Okay. So terminology. A function that looks like this we're going to call, a function that looks like this we're going to call concave up. concave up. Function looks like this, concave down. Mathematicians really don't use this terminology outside of calculus. We call this convex. And then we say that this is concave. I'm going to give the mathematical definition of concave up in just a moment. But in calculus, if f is differentiable, and now we're going to need multiple times differentiable. So if it has multiple derivatives, so if f is I'm sorry? Multi-differentiable, that's right. So here it's called C2. You need two derivatives. If f is twice differentiable, and f double prime is greater than 0, then f is concave. Most of the functions we'll deal with will have all sorts of derivatives. And the reason is because when we model real life, well, first of all, most phenomena are pretty continuous and differentiable, right? Those people who have to deal with the temperature at a particular place when lightning strikes, they have a lot of problems, right? That's a non-continuous differentiable issue, right? But for the most part, when we model things, they're with nice smooth functions. And so similarly, if f double prime is negative, then f is concave down. Here's the mathematical definition. Of concave up or down. So the street version in calculus is that a function is concave up if it looks like a U, right? Concave down if it looks like an upside down U. How do we say that in general, right? So, but in calculus, things need to be smooth. And so we're going to say that this is concave. What is that?
Down.
That's concave down. This one is concave up. This one here. Right, so in calculus we would say that is, we're not even going to talk about that, right? In calculus that's not differentiable in the whole thing. Okay. But in general, we would like to say that if this is concave up in mathematics, in general mathematics, if this is concave up, then so is this. So that concavity has nothing to do, or convexity has nothing to do with the second derivative in general. What makes this concave up, right? So what makes it concave up is that if you take any 2 points on the graph, what happens? What do I know about this line? Well, not only that in this particular case, but this line is always inside the graph. That's what makes it concave. So, or I should say this line is always above the graph, whatever that means, right? So take any 2 points that the line connecting them is above the graph, right? And so what makes this concave down is that you take any 2 points and it's under the maximum or the minimum, right? To do it in terms of calculus, it always means that the tangent line is always under the graph. That makes it concave. Well, in this case, it's concave down because the tangent line is always above the graph. This one is concave up because the tangent line is always under the graph. Okay. Those are other ways of talking about it. So that's an aside. But for us, things will be nice and smooth so you can determine it fully because of the second derivative. We'll have tons of applications for the second derivative. But the first is the second derivative test. For local max. Local max. It says this. It says, yo, I'm going to give you a place. Here's F. Here's C. I'm going to tell you you're flat at C. Okay. So F prime of C is equal to 0. The question is, am I at the top? Am I at a hump or not? If I'm at a hump, am I at the top or at the bottom? Right, I'm going to give you a piece of information. I'm going to tell you that F double prime of C is positive. Are you at the top or the bottom? Bottom. Why? Because it's concave up and you look like a U. So it's got to look like that. It's just that simple. So knowing that you're flat and then the concavity, whether you're concave up or down, is enough for me to know. Right? That's the second derivative test. Right? So you can bypass the first derivative chart nonsense if you are smooth enough and have a second derivative. And then you can go ahead and just plug in C into the derivative, get 0. And if you are brave enough to take one more derivative and plug in C, if you get something positive, you're at a minimum. And similarly, if F double prime of C was negative, at C was negative, then you would have something like this, and it would be a maximum. That is the second derivative test. We'll state it now. The second derivative test. If F prime of C is 0 and F double prime of C is positive, then F of C, oh my goodness, let's just be clear what in the world is going on. This is not something to be taken for granted. This is the whole point of calculus, right? That again, saying something about the rates of F tell me something about F, right? That we have some function that we don't know about, and then I can, if you tell me some things about how its derivatives, I can tell you about that function. That's crucial, right? F of C is a what? Is a minimum. If F prime of C is 0 and you look like an upside down U, then you better be at the top. That's the street version. That's the second test. F of x equal to, we'll do this in a couple ways. Yes, please.
How do we know when to use the first derivative test over the second?
That's a great question. And so it's your choice, right? As we were saying before, usually if I don't want to take the second derivative, right? So I'm going to give you some function like the square root of x squared minus 4, right? I'm probably going to use the first derivative because I want to take one derivative, find some places, and then I just don't want to do another derivative of that, right? So it's a matter of, sometimes you don't have a second derivative and you just have to use the first derivative test. Other times, like for this polynomial I'm about to put, I probably would prefer to do the second derivative test because taking one more derivative of a polynomial is very easy, right? So let's do this polynomial. So it's a matter of taste. On the test, I'll ask you to use both, right? So that means I'm probably going to give you a polynomial and say use both tests. So I'm not testing necessarily on your ability to take the derivative. I'm testing on your ability to use both tests. So let me mimic that right now. I want you to find local max and local min using, and I'm probably going to ask the whole 9 yards, right? So 1/3 x to the third minus x plus 5, right? Here's the full blown out, roughly question I'll ask. For this function, find where f is increasing and decreasing. Find where, I'm writing this kind of out of order, find where f has a horizontal tangent. Find local extrema. Right, so I just introduced that term. Don't be intimidated. Local max or min. So using the first derivative test, find where f is concave up, down, find where f changes concavity, and then find local extrema using the second derivative test. For that function. Please go ahead.
For part C, do you mean like the y value?
Say it again.
For part C, like are you asking for the y value?
Yes, that's right. What are the local maximum and minimum values? What are they? X cubed, 1/3 x cubed minus x plus 5. Get to it. You'll need to find the derivative set equal to 0, solve, blah, 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 blah. Absolutely. 1/3 x cubed minus x plus 5. Looking for those places. Looking for those places. And all that intervals and all that stuff, right? We're going back here. So we'll get to the. Go ahead.
Is this just to figure out how to graph a function without using a graph?
We can do that. Yeah. So there's a whole section on curve sketching. I'll take a look at it and see how in-depth it goes. I'm not that interested in curve sketching in that sense that much. We will do some curve sketching.
So why'd you make the sections?
Say it again?
You said what was the reason for the steps again? The reason for the steps?
Oh, no. Oh, that. So I'm giving this problem to test the first derivative test, the second derivative test, and whether you know how to find where f is increasing, decreasing, and so forth using the derivative. Go ahead, please. Yes. Down here or up? Up. We'll probably get the C doing this with the time we have left today. Of course, we're going to take a derivative, set it equal to 0, and solve. F prime of x is equal to x squared minus 1. I set that up nicely for you all. This is 0 and x is 1 or minus 1. We're now going to set up a number line. This is my first number line of the day that had more than one value on it. It's x squared minus 1 is the derivative, and we need to pick values. Let's pick 10, 0, -5. Plug those values into the derivative, please.
So when we test values, do you want to see the word for, or like if we know that it's positive, we just put like a sign?
We'll have to rely on Jessica. I don't know how she's going to grade it. Yeah, so, or you could just go ahead and take the extra 5 seconds and do it. Yeah, I mean, so I know I'm sorry to disappoint you. But again, in the future, you're going to be in context where you may not even have the chance to ask how it's going to be graded. Just write it so that no grader can mark it wrong. Just fully, I know, I love rolled eyes. They're the greatest thing ever. But I love brilliant people. Fully realize your potential and just write everything perfectly, right? Go ahead.
If I was planning on increasing, because I know there are 2 intervals where it is, between the 2 intervals, do I put a union, or is it something else?
Let's write how we want the answer to be. So, and we'll end with A. We'll end with this, and we'll come back here tomorrow. So I am now in a context where it looks like when you plug in these numbers, we have -1, 1. I chose 10, 0, -5, right? -5 squared minus 1 is 24, which is positive, increasing. 0 squared minus 1 is -1, negative. 10 squared minus 1, 99, positive. The derivative is positive over here, whatever that means. It's negative here, and it's positive here. F, therefore, is increasing here, decreasing there, and increasing there. If you wanted to find a place where the function was increasing, it would be on this interval, or it would be on this interval.
So would there be a union sign?
That's how we say or in mathematics. So F is increasing on this interval, union with this interval. F is decreasing, F increasing in the interval. F is decreasing where the derivative is negative, that would be on this interval. F is decreasing where the derivative is negative on the interval -1 and 1. From this chart alone, we'll be able to find where F has local maxes and local mins. At -1, we have a local maximum because F is increasing before -1, and then all of a sudden it starts decreasing after -1. That is the first derivative test, and then F goes from decreasing before 1 to increasing after 1. That makes 1 a place where there is a local minimum. Well, in there. Tomorrow we'll finish this problem, and then we'll do some applications, word problems. I'll try and intimidate you, but I can't. I can't intimidate you.
extra credit, actually.
What?
My extra credit.
Oh yeah, I can pass it on next time.
Oh,
Yeah.
thank you.
Yeah. Oh, you're very welcome.